Assalamu alaikum everyone. So in the previous session we have discussed a lot of concepts like what is Gaussian elimination and how to find a solution to the equations. So today now we'll go into the meat of linear algebra. So we'll go into vector spaces. So I have been using these terms since lecture 1, something called as vector spaces. Now today we'll go into the mathematical detail of what these things mean. Now let's move forward. So what is a vector space? So if you see it, so you have been seeing me drawing these planes like this, drawing a xy plane in which one axis is x-axis and other is y-axis. So I call this as R2, something as R2, and maybe I also draw a number line like this in which I just describe any vector or maybe we'll call that a scalar by just one number like this 0 or maybe 1. This is 0 and this is 1, 2 and things like that. So we call this R1. Similarly, this is our R2. Why this R? Because each entry here is a real number. So that's the reason I am putting this R, and 1 basically means the dimensions, so how many components that it have. So if you see this vector, so it is only one component. If I write R2, R2 can be written as 2, 3. So this means it has two components, one along the x-axis and one along the y-axis. Similarly, if you see R3, R4, Rn and things like that. Until this point of time, I used to call them a vector space. Okay, now let me formally tell you what a vector space is. So I will just restrict myself to these real numbers. So there can be other numbers, complex numbers, and there can be what are called as fields. So I'll restrict myself to this real numbers. So I told you that these vector spaces, they can be the functions, they can be what are called as fields and stuff like that, but we'll restrict our discussion on these real numbers. So if you know that in a vector space there are vectors. So vectors basically are nothing, if you talk in programming lingo, that the lists that we had. So a vector space, it must have two operations with it. The first is called as addition, and then the second is called as multiplication with a scalar. So first we should have what's called as a field. So here the field is real numbers. So first we should have this real numbers. In technical terms, we call it a field. So we don't need to define field, but just remember that these vector space are defined what is called as fields. So we have real numbers. Then on top of that, we have two operations. The first operation we have is called as addition, and we call it vector addition. We have seen details of these operations. Now I am going to formalize the things. What is the meaning of a vector space? Then we have this scalar multiplication. Scalar multiplication. So what is a vector space now? So roughly I can say that if you take any two vectors, so if you take any two vectors, let's call them v1 and v2, which belong to our vector space, let's call that capital V. This is our V. So V basically is the combination of these things. So we call it a vector space. So now how to discuss it? If we can add these two vectors, if we can add these vectors v1 plus v2, and still that addition belongs to this vector space. Okay, and if we sort of multiply any vector by scale, let's call a vector v3, and that also belongs to this vector v. Okay, this field v, basically this is our field v. So we'll call it a vector space. So vector space basically has two properties. So if we have two vectors and if we add them, so this still belongs in the v, and if we can multiply it by a scalar, it belongs into this v. Okay, so let's take an example of R2. So we'll see this if this R2 is a vector space. So R2, so we can define a lot of numbers in there. So first let's define a vector R2, that is 1, 2. Yeah, you know that this belongs to this vector space R2. Okay, then we have a vector, let's suppose 3, 4. You know that this also belongs to R2. So R2 basically is the combination of all the vectors which have two components and which have these real entries. So if we add these two vectors, so addition of these vectors is 4, 6. So you all know that this also belongs to R2. Okay, so these were some random vectors. So if you pick any two vectors from the vector space, so if you add them together, so that entry should still be in the vector space. The other thing is, if you multiply any vector by a scalar, let's take 3, 4. This is a vector belonging to R2. So if you multiply it by a scalar, let's suppose a number 3. So this is equal to 9 and 12. So this, you know, also belongs to this R2. Now these have some properties. So these are the two crucial properties. Now mathematically we'll define what are the properties that a vector space should obey. So why am I telling all these properties? Because the point is that when you will be learning about the things there, you will have to consider, is it a vector space even? So from that it should be clear. So we have two things now. We have addition, that is the vector addition, and then we have the scalar multiplication. So the first thing is, if we add any two vectors x plus y and y plus x, they should be following this commutative property. That is in regards to this plus operation. Okay, that's the first property. And the second property that we have is associativity. X plus y plus z must be equal to x plus y plus z. This is associativity. So that means if you first club these two vectors and then add this x, it should be equal to, if you club x plus y first and then add the z, they should be equal. Then the third property is that there should be a unique vector which we call as zero vector. So there should be a vector which we will call as zero vector. So if this vector is added to any other vector, let's suppose we have a vector x. So if this zero vector is added to this vector, any vector x, so it should give the result x back. So that's the property we should have. So this is the other property that we have in terms of addition. And one more property that we should have in with this addition is that there should be an inverse. So what is the meaning of inverse? So if there is a vector x, okay, then there should be an inverse of this minus x, let's call that. So if we sort of add them together, x plus minus x, so they should give us the zero vector. This is the fourth property. So what is the fourth property? The fourth property is that there should be a unique vector which we call as inverse of this. So inverse basically means, so if we have this x and then we have this minus x, so this basically should have this inverse. So if we add them together, it should give us the zero vector. Let me pause here for a second if you have any questions regarding the operations, and I'll fix my screen. Is it clear? Can somebody speak?
Yes, sir.
Yes, sir.
So now we are going to the mathematical details. That's the reason I want you to understand this fully, because I had a discussion with you guys that whenever you are facing an interview, so there they'll ask you mathematical questions. They won't ask you a question directly. So there you might be facing a question: what is a vector space? What do you mean by a vector space mathematically? So that time you must know it. So that's the reason I decided you to like cover all the concepts in algebra. It's okay to take 2 to 3 more sessions, because this will sort of give you a broader overview of what we are going to see in this. So if your maths is concrete, if your maths is clear, and the other concepts of deep learning and machine learning will become really easy. So this is the first thing with respect to this plus operation. Then we have the other operation that is defined on that field. The field here we'll consider is real numbers. So there are different fields as well. So that is the scalar product. So the first thing is we should have a vector called as identity. So here it was inverse. So this was inverse. Inverse. We call it an existence of inverse. For each element there should be an inverse. If you take any vector x, so there should be an inverse. So similarly, the fifth property, that property is with regards to this scalar multiplication. We should have an element identity element. Let's call that 1. And basically this is an identity element. This should be an identity element. So what should you do if you sort of scalar multiply this 1 with any vector? Let's suppose we have that vector v1. This should give me v1. Okay. This is the other property with respect to this dot, with respect to the scalar multiplication. Then let's suppose the sixth property is if we have two scalars, c1 and c2 are two scalars, let's suppose. If they are two scalars and we have a vector v1. So if we multiply this c2 with the v1 first, and basically we are scaling this v1, and then scale it again by c1. It should be basically equal to, if you multiply c1 and c2 together, then scale the vector with the constant, that with the scalar that you got. Okay. So this is with respect to this dot, this scalar multiplication. And the seventh property that we have is that if we have two vectors, let's call them v1 and v2. If you add them together and multiply it by c1, it should basically be equal to c1 v1 plus c2 v2. We should distribute the scalar. This is called as distributivity. So we should be able to distribute. So we should be able to distribute this scalar with these vectors by if we have a plus sign in here. So this should be obeyed. Then the similar thing, if we have two constants, let's call them c1 plus c2, and if we have a vector v1, this should be equal to, if we sort of first multiply it with v1, the c1 should be multiplied by v1 plus c2 with v2. So these are the properties that should be followed when we define. So in the vector space, again to reiterate what we have a field, we have a field of real numbers here, so this is R. Then we have two operations. This is called as vector addition. Then we have vector scalar multiplication. So for each of these operations, there are some properties that must be followed. So let's see if R2 is a vector space. If this R2 is a vector space, so R2 basically means any vector which has real entries in this. The first thing is, if you see, so we have defined this plus operation and the dot operation as well previously. So if you see, the first property is obeyed by R2, second property is also obeyed by R2, and there is zero vector. If you call this 0 0, it's a zero vector in R2, so this property is also obeyed. For each element there is an inverse. Why? If we have a vector 1 2, so there is -1 -2 is its inverse. So existence of inverse is there in R2. So if you have this v1, so there are vector v1 which you will multiply. For example, this 1 1 is a vector. If you multiply it with any vector, it will give that vector back. It will give you this v1 and R2 back. So it also has this existence of identity. Then if we can take any constant, let's suppose we'll take constant c2 and then multiply it with v1. Let's take an example. So here let's suppose we have a vector 1 2, so we multiply it with 2 first, so we'll get 2 4. So if we multiply this by 3, so we'll basically get 6 and 12. So this is our final vector. So what I told you, that if you take this and multiply them together first, so this will be 6, then you take the original vector we had. So original vector was 1 2, so this will also get result as 6 12. So this property is also satisfied, this property, sixth property. And seventh and eighth, you can prove them accordingly. So we now established how to check for a vector space. If you are given any vector space that we have operations defined, this plus and dot defined onto that, so you can sort of get the you can sort of derive it mathematically whether it is a vector space or not. But just keep two things in mind. So all these properties are captured in two things. The first thing is, if we have this vector, random vector v1, or let's suppose we take a random vector v1 and random vector v2, if we add them together, if we add these vectors together, v3 should also be in the same vector space if we get v3 out of these vectors. So if we have v1, so if you just get some vector v2 out of this, so this v2 should also belong to the vector space. What are the vector spaces? So these are the two properties that you must keep in mind in order to check for this, because you can sometimes you may not be able to check all the 8 properties. So this is basically equivalent to this. So if you can just check for these two things, so this is equivalent to checking all the 8 properties that I discussed right now. So is the concept of vector space is clear now? What is the vector space?
Yes, sir.
Nice. So if it's clear, then I can move on to the next topic. So can you tell me that is R3 a vector space? Is R3 a vector space? Now you don't have to check all the 8 properties. I just told you two things to check because they're equivalent. This is left hand exercise for you to prove their equivalence. This is really easy to prove the equivalence. So R3 basically means in which a vector we have real numbers over here. We have real number 1, real number 2, and real number 3. So this should be a vector space. Why? If you take any two real numbers, if you add them, it will give a real number having 3 components. So existence of inverse, everything is there. But if you add random, take x, y, z, let's suppose this is a vector in R3 in which these entries are real. So if you take x dash, y dash, z dash as other vector, so if you sort of add two real numbers, you know that these real, again the real addition of two real numbers is real. So this property is followed. So if you know that multiplication of a real number with a real number also gives a real number, so this property is also followed. So you can see that R3 is a vector space. Okay. Now let's go to the concept of subspaces. Subspaces. If the concept of vector space is clear, and this really becomes important, because why is the concept of subspace is clear? Because we'll be projecting onto a subspace. That time I won't be telling you what subspace is. I'll assume that you know what is the meaning of subspace. So again, what subspace means, so here we have this space, so it again should be a vector space. And here there's a word sub. Basically, it should be a subset of some vector space, but it itself should be a vector space. Okay, I told you to check only for two properties if you want to check for the web space, for the vector space. So what is the property? The first property is that if you add any two vectors at random from that vector space, the addition, the resultant vector should be present in that vector space. And similarly, if you multiply it by a scalar, that also should be present in this property. Is sometimes called as closure property. We call that it is closed under addition, it is closed under scalar multiplication. So these are the properties you must remember. Okay, so why is it called a closure property? Let's suppose, for example, if we have the number of integers, let's suppose we have 1 2 3 4 5 6 and so on, like -1 -2 -3. So you know that if we sort of add these integers together, again it will give an integer from this set. So this is the set of integers. So if we add them together, so it will again give me an integer. So we call that integers are closed under the operation addition. Because if you see that if you take any two integers, like suppose 1 plus 2, that's 3. 3 is also a part of that set. So this is called as closure property. So the integers are closed under this additions. In the similar fashion, if you multiply any integer by any other integer, that will still give us integer. So for example, 2 multiplied by 4 is equal to 8. This also belongs to this. So this is called as closure property. So here the closure property should be followed. Again, coming back to the subspaces, so it should be a vector space itself, and it should be a subset of some other bigger vector space. Okay. So if I take an example, let's suppose we have this R2 vector space. You know that R2 is a vector space. So can I call that R1 is a subspace? R1 is a subspace of this. That's the first thing I need to tell you. Is R1 a subspace? The thing that you can check is you can take any two vectors from this at random. Let's suppose V1 and V2, and you can add it. If you add V1 plus V2, okay, that should basically give you some vector v3. Is this v3 present in this r1? Obviously it is, because it is like real numbers. If you add two real numbers, you'll basically get a real number. Similarly, if you take a random vector v4 and you multiply it by any scalar c, that's a real number, so you'll again get a thing from here. So it basically is a first thing, it is a vector, it itself is a vector space. Okay, now you know that why is it a subspace of this, because it's a subset. You can write any r1 like this, write r in here and other entry as 0. So this is a subspace of these. All these vectors which have the other second component as 0, they'll come to this r1. Maybe the r1 we can write r1 like this, r only. So in r2 we can write the second component is nothing, 0. So we can write the other component like this, r0. So you know that now we can call this r1 a subspace of r2, because you know r1 it itself is a vector space, and this r2 is also a vector space, and this is a smaller vector space. A vector 1 2, it does not belong to r, but it belongs to r2. So any vector that belongs to r1 also belongs to this r2. That's why we call it a subspace. So is the concept of subspace is clear?
Yes, sir.
Okay, so can you tell me, is this 0 0 vector a subspace of r2, or maybe just a 0 vector, is this a subspace of r2? This is just one vector. Okay, so R3 has a subspace. R2 is all, R3 is its own subspace. R2 is also its subspace. R1 is also its subspace, and 0 vector is also subspace. So we'll establish that if there is a subspace, let's suppose R cube, and I'll subtract 0 from it. Let's suppose I'll subtract the 0 vector. Let's call this as an S. Will you call this S as a subspace now? I'm just removing one vector out of it. It's like if we have R2 like this, R2 is a whole plane. I'm just puncturing this. I'm just putting a hole over here. This 0 0 vector does not exist there. So can you still say that this R3, this R2 basically, let's suppose this is R2. So this R2 is still a vector space. What do you say? So Salim, Amir, Umar, can you give the reasoning? Why do you say that this still is a subspace? This still is a subspace of R2, or maybe a vector space? Let's start with Amir. Why do you think that this is a subspace?
सर जो इसका सर सबस्पेस तो फिर भी रहेगा ना, रियल नंबर ही आएगा.
But you have to check for the properties. Let's suppose I'll take a vector 1 2. You know that belongs to R2. Yeah, R2 में belong करता है. Now I'll take a vector -1 -2. So what I told you is that if you add these vectors together, that vector should also belong to this. So here now we got 0 0 vector. You know that that does not belong to this S. Did you get my point?
यस सर.
So is it a subspace of R2 now?
नो सर.
So it is not. So that establishes a point that 0 vector must be present. So this 0 vector must be present. So that's the reason I haven't told you in these properties. So if you again sort of remember these properties, I told you that there should be a 0 vector. The existence of 0 should be there. So if it is not there, so we can straight away say that either based on these properties or based on this rule, if based on the closure property, we can directly say this is not a subspace. Is the concept of vector space and subspace clear? Now I can move forward with that now. But do not get the things oversighted. Like what are we actually dealing with? We are dealing with the linear equations. and you saw the intuition how they are defined by planes, hyperplanes, and things like that. Do not get that out of your head. Just keep that in the back of the mind. Now we are just adding a level of abstraction. We are not always thinking in those planes and things, but we are thinking in terms of numbers. Okay, that is the only abstraction I want you to have. But do not get the oversight of this thing that we are solving something else now. The same picture is that we showed in the earlier lectures in which we had those visualizations, but now we are doing it mathematically and we are just playing with numbers now. Okay, so now we can move forward. So why was I teaching you the vector spaces, subspaces? Because there are two important subspaces. One is called as column space. One is called as column space. So what is this column space? Let's define it first, then we'll see another subspace that's called as null space. These are really two important things. Okay, so as you know that if we have a matrix A, so A matrix basically can be the copy. If you write those equations, we have, let's suppose we have equations like this: 1u plus 0v is equal to, let's suppose, some 3. Then we can have an equation 5u plus 4v is equal to some 2, 2v plus, let's suppose, 4v is equal to 9. So we can have an equation like this. So we can get the coefficients, only coefficients from this A. So A will be 1, 5, 2, 0, 4, 4. So this will be the coefficient matrix from these equations. And you know that we have these unknowns that can be u, v. These are the unknowns. And then we have these b's which we need to find. This can be 3 to 9. But we are focused on this. The whole goal is to find this u and v. So first thing is we'll see what a column space is. So any matrix, you know that what it defines. So any matrix basically is a set of homogeneous linear equations. That's what it defines. So we call this a coefficient matrix. So now if you take a linear combination of all the columns that we have in the matrix, so we take all the linear combinations. So you'll take 1 column 1 plus b column 2. So you took a column 1 plus b column 2. So you get some vectors. So you get a set of vectors here. Set of vectors. Okay, if you get a set of vectors, we call those set of vectors as column space. Column space. Now the question remains, is it a vector space? That's a question. So is it a vector space? That remains as a question. So we'll get a bunch of vectors from here. Okay, if we add these two vectors, so let's suppose I'll get c1 plus c2, and because this is the column 1, let's call this column 1, let's call this column 2, and we can we'll extend it to the nd then. So let's have this coefficients as a1 and b1. So let's suppose this the vector, this is basically what I mean by, this is a generic S. S basically I call the set of vectors which I call as column space. Let's take two random vectors. This maybe we'll take two random vectors v1 and v2. So in v1 what we can do is I'll take 1 times c1 plus 2 times c2. Okay. So v2, let's take 3 times c1 plus 8 times c2. So in order to check if these vectors, if still s, if s contains addition of these two, what we can do is we can just add them together. So if we added them together, what we'll get is we'll get 4 times c1 plus 10 times c2, 16 yeah, 10 times c2. This is what we'll get. So you know that you can just multiply 4 and 10 with this with the columns that we have, 4 and 10 with the columns of c1 and c2, and add them together. So this also belongs to the S. So we can check that is this set of vectors that we got by taking the linear combination is really a vector space. And then you can even multiply any vector by a scalar, still you will find that that vector belongs here. So do you understand? The first definition is what is a column space. Column space is if you take a linear combination of the columns of any matrix. So we call that a column space of that matrix. So here column space of A basically is you take linear combination, let's suppose C A1 C1 plus A2 C2 and so on. This we call as a column space mathematically. And now I also showed you that it also is a vector space. Okay, so this is the vector space basically. So is it clear? What is the concept of column? Is it clear? Is
सर
it
ये
clear?
रिपीट करना थोड़ा.
Again, to tell you, if we have columns of these, if you know about linear combination, we have been taking linear combinations from day one. So linear combinations basically are take some combination of this column and take some combination of this column. Okay, if you now take all the combinations of these two columns, so it will give us a bunch of vectors. So for example, we have 1 5 2, again taking this example. So we had vectors 1 5 2. This was one column of matrix A. Then we had the other vector as 0 4 4. Okay, so if you take all the combinations, the combination can be, let's suppose 1 times of 1 5 2 and plus 1 times of 0, 4, 4. This will basically give us 1, 9 and 6. So this is also a vector. Okay, so again, if you change these coefficients, let's suppose to 0 and 1, so you'll get 0, 4, 4. If you change these coefficients again to some other number, so you'll get some other vectors and so on. So all these vectors will form a set, will basically form a set, and I proved that set is a vector space. So what I told you, column spaces, if you take linear combination, all the linear combination of these columns, we call it a column space. Is it clear now?
Yes, sir.
So how will it look visually? So let's suppose we'll take the example of R2. So we had a vector 1, 5, 2. Let's suppose in the R3. So let's suppose it's like this 1, 5, 2. This was a one vector. So other vector, let's suppose, was 0, 4, 4. Let's suppose it was like this 0, 4, 4. I'm making random arrows. So you know that if you take all the linear combination of these, so you'll basically get a plane like this. So you'll get all the vectors from here, here, here. So you'll get every point. Okay, from here. So so these vectors were in R3. This is also in R3. So if you take the combination of all of these, you will get the column space. The column space, we can call it, is this plane. Okay, is it passing through origin? Yes, it should pass through origin, because if you take 0, 0 in the coefficients here, so the 0, 0 vector should be there. So it should pass basically through origin. So this is the origin, it should pass through that, because I told you for a vector space to be a vector space, the origin must be present there. So this is the column space of A, visually speaking, if I need to define what a column space is. Okay, is it clear?
Yes, sir.
Nice. So now you say, why is this column space important? So let me tell you the importance of column space. Importance of column space. So why are we defining it? Why are we taking this much of time to explain these things? So you know that the basic equation is ax plus b. Ax is equal to b, sorry. Ax is equal to b. That's the equation we are solving. Okay? And we want to see whether it has a solution, whether this thing has a solution or not. Can we find such x's so that if we just multiply this A matrix with that x, and it should be equal to b. So it's easy to tell now. If this B does belong to the column space of A, then there is a solution. If this B does not belong to the column space of A, then there is no solution. You cannot find a solution. Is it clear? There's a simple statement, but just think about it. So I told you that we had two vectors. This was a vector and this was the vector. So it basically had the column space like this. This, the whole plane was its column space. So this was the column space of it. So I told you, let's suppose there is a vector coming out of this plane. Okay, now you cannot reach this blue vector or whatever, purple vector, whatever this color is, by using these two vectors. You cannot take any linear combination and get to this vector. So we say that if I have an equation ax is equal to b, so if I am putting I am putting any value to the x and multiplying it with the a, and I can never reach b, so the answers to this equation will only be in the column space of this a. Let me take a concrete example. So again, the example here that we took is 152 and 044. 152 and 044. So these are two vectors. So can you tell me that, because these are vectors from in R3. So if you see, these are vectors in R3. So can you tell me that is every R3 possible? Can we reach any possible vector by using these two columns? Can we basically reach any vector? Just give me yes no answer. I don't want you to explain. It's whatever your intuition is. Okay. So you're telling we can reach every vector. So that shows me that you haven't understood the column space correctly. So you know that R3 basically is like a cuboid, like this. So R3 basically fills the whole volume. So I even showed you like this. If you take only these two vectors, this vector and this vector, it will just fill a plane. It won't be able to reach many vectors. It won't be able to reach all the way. It will just be a plane among this, because we had one vector like this, we had a vector like this, and we had another vector like this. So when we sort of took all the combinations, so it just made a plane out of it. So you now know that this is a subspace of this bigger picture. If you see this bigger one, so it cannot reach all the vectors in R3. So you cannot solve ax plus b for b belongs to R3. You cannot solve it for all the values. You can just solve it for the values who lie on this plane, who lie on the plane, who lie on the column space basically. The vectors which were spanned. I actually explained the concept of span, which is spanned by these two vectors. How many of you agree that we cannot create all the combinations from these two vectors now? Because visually I showed you that. Visually I showed you the R3 basically is a cube. It is filling 3D space. So when you have this one vector and the second vector, it basically was just filling the plane. It cannot fill R3. It will just fill R2. In order to get the access to the cube, you must have one more dimension. Okay, so you cannot solve this equation for all the R3. You can solve it for only the vectors which are present in a column space. So that's why I took this much amount of work to just explain the concept of column space. So if you ask me, if there is an equation, if there is a set of equations ax is equal b, so you are telling me that for which b will the axis exist. So for which b's will I find the value of axis, so that I get, if I multiply those axes with a, I'll get b. I'll tell you that the b, it must be present in the column space of a. For those values, this equation can be basically solved. Otherwise, it won't have a solution. Is it clear? Really nice. So if you're understanding these things, so this is why now we are abstracting out from those things, from the animations and stuff. Now we are just playing with the numbers. So anytime if you're asked a question, can you solve an equation? So let's suppose we are given an equation: 2x plus 3y is equal to 4, 5x plus 9y is equal to 6. So you're giving you're let's suppose given this equation. So somebody tells you that, will this be able to solve this equation? The first thing is you will say 2, 5, 3, 9 is the coefficient matrix, and we have this xy. So we have this 4, 6 over here. Okay, so this is the matrix representation. If this vector 4, 6, if this vector 4, 6, if it belongs to column space of A, then yes, it can be solved. So we can find some values of x and y which will basically satisfy these equations. By satisfy, I mean if I put that value of x and put that value of y, I should get this equation as checked, and I should get the similar for this equation as well. So what I'm saying is, if somebody gives you a bunch of equations and tells you, is there a solution for that, what you can do is, you can tell them, if the solution, if the resultant vector that you want belongs to the column space of this A, then the solution will exist. So here you know that these two vectors are what we call as linearly independent, so they'll span whole of the 2D. So, and this vector is in 2D, so yes, there is a solution, because you know that these two vectors are independent. So 2, 5, let's suppose, will be like this, and this 3, 9 will be like this. So if you take all the linear combinations of these vectors, so they'll again span the whole space. They'll span the whole space of 2D plane. Okay. So you'll get this vector as well. You can get this vector. You can get this vector. You can get this vector. You can get any vector from these things. So 4, 6 basically lies on the plane now. Okay. So you can get this 4, 6 out of this. So here, why couldn't we reach everything? Because here we had these two columns only, and you know that in order to basically span whole of the 3D, you must have three vectors at least, and these three vectors should be independent. That's the reason, if we had only two vectors, they'll just span one plane, and many other vectors can't be reached from that. So there will be very few of these b's for which we can find the value of x's. But in this case, you had complete equations. So that's why sometimes I tell you, we should have n equations and n unknowns. Okay, if we have n equations and n unknowns, and for that we can find a solution, but the condition is that that should belong to the column space, that it should belong to the column space of A. The column space basically means the coefficient matrix of this equations. Can I move ahead now?
Yes, sir.
Nice. Now we'll see what is called as a null space. This again is a very important concept. So you saw what is the meaning usage of that, but when we'll be going in the further lectures, you'll understand, you'll all the pictures sort of will, all these pieces will sort of form a picture and whole picture. That's the reason I'm telling you that you must revise these lectures again and again, because algebra, linear algebra, it is the fundamental building block of the machine learning, deep learning. If somebody understands this, he has a really high chance of understanding what is going on in machine learning, deep learning. So I think in this session itself, or in the next session, we'll cover the first algorithm of machine learning only by using the algebra. So you will be writing the whole code of algebra, and then you will be able to make a classifier out of that. We'll just when we go on to this projection, and we'll learn about what's called a linear regression, the first algorithm, and that's totally based on this matrix multiplication and this concept that we are going through now. The next concept I'll take is null space. Okay, it is denoted as null space of A, n of A. So what is the null space now? Okay, now you have this equation which we had, ax is equal to b. Now I sort of assume that you understand what is the meaning of a square is b. Now our concern was, can we solve it for b? Can we solve it for every b? Let's suppose we'll make this b as 0. So we'll make this b as 0. So we'll have an equation like ax is equal to 0. So the question basically is, if you have this matrix is basically a linear transformation. If you again go back to the visualizations, so what this linear transformation does to vectors, so it will take many of the vectors to 0. Okay, if you take a linear transformation, it takes many of the vectors to 0. So these will be a set of vectors which the linear transformation takes to 0. So I want to find that set of vectors. So I want to find the set of vectors which this a takes to 0. Okay, so if you see, if you have those pictures in your head, so we used to have a transformation. This a basically was a transformation. There are a bunch of vectors which might go to 0. Okay, there can be only one vector, there can be a lot of vectors which go to 0, but for sure 0 0 vector always goes to 0. So if you have a 0 vector, so if you have any matrix a, you multiply it by 0 vector, you will get 0. So for sure we have this one vector going to 0, but there are some other vectors that also go to 0. Okay, for example, let me take an example. If I have a matrix, let me make cook up an example. I have 1 5 2 0 4 4. Okay, and I want to find values of uv such that it becomes 0 0 0. So I want to find the values of this uv. I want to find the values so that it becomes 0 0 0. The first thing I can directly do is, I can maybe just write 0 0 over here. That's a trivial vector that belongs to this, that basically this matrix takes to the 0. Is there another value which I can take it to 0? Mm-hmm. Maybe I need to think a bit. So in order to get this uv as non-zero vectors, but there will be vectors. Okay, maybe in the subsequent examples we'll get those when we'll finding how to find the null space. So my point here is, this matrix A, it takes a lot of vectors to 0. So all these vectors will form a set. Okay, that set of vectors is called a null space. So if you ask me how to define a null space, so I'll tell you, the matrix consisting of different rows, all these rows will take some vector, all these columns will take some vectors to basically 0. So that set of vectors is called a null space. Okay, so now what is null space? So null space contain vectors which after multiplication or transformation with a become 0. So all these vectors which after application of a onto those vectors, they became 0. So we call that a null space n of a. So now the point is it a vector space? That's the question, because I'm using this space term in here. If you see, I'm using this space. Okay, now in order to prove null space, so what I'm telling you, let's suppose we have an x1 vector and we have an x2 vector. Both of these, let's suppose, belong to the null space of a. So from this I can say that if that matrix is a of x1 is 0. Okay, and from this I can conclude that a of x2 is 0. So what I want to see, I want to see if I take x1 plus x2, does it also belong to null space of a? This is what I want to prove. The simple proof. So you can just add these things together. You can say a x1 plus a x2, a x2. As you know that this thing is equal to 0, this thing is equal to, so it is equal to 0. Okay, so this thing is equal to 0. Now you can take the a common, because we have studied the distributivity law. So this is x1 plus x2 is equal to 0. Now this vector also belongs to the null space of a. A simple proof. Okay, so if we have a vector x1, if this belongs to null space of a, let's have a scalar c. So I am saying if c x1 should also belong to this null space of a. So how to prove this? Again, a simple proof. So I'll just have, from this I can say ax1 is basically equal to 0. Okay, so now if I multiply this, so I can multiply this thing. I can say a c x1. Okay, now I know that this portion, so I can just multiply both sides by c, multiplying this side by c, multiplying this side by c. So I can say c x1 is equal to 0, c basically means 0. So what I can say is, you know that this portion is also equal. So I can just take this c and divide it over here. So it will be ax1 is equal to 0. So again, yes. So c1 x1 basically is equal to 0. So because if we just sort of give this value, we all again arrived at this result. So what I'm saying you that a c x1 also is equal to 0. If the x1 belongs to the null space, the Cx1 also belongs to null space. So here I can say that this is a vector space itself. So again, to reiterate, what is the null space? So null space is are the vectors, is a set of vectors which are taken to the zero after applying the transformation. Okay, so null space of matrix consists all the vectors of x such that ax is equal to 0. If you ask me mathematically, so all the vectors for which ax is equal to 0, all these x's, okay, so it will be a set of values from this where this ax is equal to 0 will be a null space. Is it clear? Is the concept of null space
Yes,
is
sir.
clear? Now we have two important subspaces that we saw, a column space and a null space. The column space says basically the span. If we have a matrix, what is the span of that? And this null space tells us, so okay, if after applying transformation, what are the vectors that went to 0, that basically became 0 after the transformation? Keep that two things in your mind. Now if you have these two things, by using this column space and by using this null space, the only fundamental problem of algebra is to find the solution to the system of homogeneous equations. The system of homogeneous equations is ax is equal to b. So now we sort of divide into two things. So one generic one, that is ax is equal to b, and we also did ax is equal to 0 if we have this. So many of the times you might have seen equations like this. So this we can solve and this we can solve as well. So we'll deal with this separately and we'll deal first with this. Let me take a break so that I can drink some water. Is it clear so far? Let's chit chat for a bit. Maybe you also
Yes,
became
sir.
bored by seeing the mathematical details. Am I going too
Yes,
mathy?
there.
Am I going too mathy into this? बहुत ज़्यादा मैथ तो नहीं हो रहा?
No, sir.
So I'm trying to make it as simple as possible because I told you these are the foundation building blocks of your machine learning, deep learning. So if you could understood four topics, the first topic is algebra, statistics and probability, and if you understand optimizations, that is all machine learning and deep learning. So if you are given any book, any research paper after that, maybe you'll just find it, and because equations will be written here and there, and you'll be able to understand it. So whole the machine learning is based on these four things: algebra, probability, statistics, and optimizations. This is what whole of the machine learning deep learning is there. तो इसके बगैर कुछ होता ही नहीं है deep learning machine. Maybe some like that, computer programming and stuff like that. But seeing these techniques, because these techniques were built before computers came into existence. But now what computers did is they made it faster. You can basically solve any problem by hand. But if you want to really make it faster, so what you have to do is you give the problem to the computers which do computations really faster. Nothing happens basically in the computer, it does computations faster. Otherwise, you can do machine learning, deep learning with your hand. So you can say, you can just write something and it will, you can just find a classifier. Okay, that's what people used to do. But given to the machine, it boils down to numbers and you can manipulate these numbers. Okay, let's now go solving this ax is equal to 0 and ax is equal to b. This is really important. So in the first chapter, if you see, in the first part, which I call that the first part intuition wise, where we showed this Gaussian elimination, in order to sort of uh, solve this equation, what we did is we can just write it x is equal to a inverse of b, because we saw the inverse. That time we did not find the inverse, we used the Gaussian elimination. We eliminated some variables and then did the back substitution. That was the thing. That's the simplest solution to this equation, can be just used by the elimination. Okay, now what I'll do is I'll first show you the methods of solving this ax is equal to 0. Okay, and then we'll move on to this complete solution. If we have this ax is equal to b, how to get the complete solution? The first thing is I'll get special solution. I'll get the null space. I'll get the null space of a. So, and null space plus some other solutions will give me the whole solutions. The whole point is to basically solve this equation. But in order to solve this, what I'm telling you, the first thing that we'll solve is we'll solve this equation for we'll find its null space. It's easy to find null space. Why is it easy to find? Because you need not take care of the right hand side. So if you are performing any operation onto this a, and I told you that you have to perform the same operation onto this side, but you know that it is zeros all there, so you can perform any operation. If you remember the three fundamental operations that we had, elementary operations, you can multiply a row, multiply or divide a row by any scalar. You can exchange rows. Okay, you can add two rows. Okay, that was basically these elementary operations. So if you perform these elementary operation onto these zeros, basically nothing will happen, it will still remain the zero. That's why it's some sort of easy to sort of find the solution to this. So because our goal is to find solution to equations like this, Okay, so now we'll start how to basically find a complete solution. In order to find the complete solution, we'll try to first find the null space of A. Let's go there. So we'll call it a particular solution. So here we'll call this a particular solution. This will be called a particular solution. If you want some Ax is equal B, this will be called a particular solution. So what is a particular solution? So particular solution is some, if we have a vector A, let's suppose we have some vector xp and we want to get this B. So this B will be having a particular value. So there will be a particular solution for this. Okay. So and another is called as complete solution. So complete solution basically will be if we have the solution to A and we take this, let's suppose this some x dash, it takes the solution to 0. In order to find the complete solution to this equation, Ax is equal B, so we'll take some vector xp which will take it to B, and we'll take this x dash which will take it to 0. By combination of these, we'll get, let's suppose, A multiplied by xp plus x dash. This will be equal to B, and this will give me the complete solution. I basically want to find these two, xp and x dash. So this will give me what's called as complete solutions. Complete solution. The first thing was this particular solution. If you want to find it for a particular B, any particular B, so we can just find some vector. The equation in hand was this ax is equal to B, and we want to basically find the solution. So I told you it can be split in two ways. The first thing is we can find a particular solution. So let's suppose we find some a bunch of vectors which give this result B, and then we'll find a bunch of vectors which will take every result to the 0. Then we'll add this xp and x dash, and we'll get this B solution, and we'll get this complete solution from the null space and the particular solution. Is it clear how do we get this the complete solution? Okay,
Yes, sir.
now let's take an example. Let's start an example, and then we'll see. Let's suppose we have a matrix A. Now I won't write the equations. Now you know at the background everything is an equation. So 1 2 minus 1, 3 6 minus 3, 3 9 3, 2 7 4. So it is ax plus ax is equal to 0. This is what I want to solve. That's the thing. So what I can do is I can again use the Gaussian elimination. I can again use the Gaussian elimination. Okay, so in the Gaussian elimination, what's the first step? I'll make this 0. This is called as pivot, the first pivot. So this is called as pivot, and sometimes people pronounce this pivot. So I'll call it a pivot. So this is my first pivot. By using this pivot, I'll make these entries as 0. Okay. Then I'll take this after the transformation, after whatever I did. So I'll take this as second pivot. Okay, then maybe there is no need of third pivot because we don't have to make other entries as 0. The goal was to make the upper triangular matrix here. Upper triangular matrix when we used Gaussian elimination. So here we'll make what is called as echelon form. So we'll make what is called as echelon form. So I'll tell you what echelon form means. So echelon form basically means if there are some numbers like this and then the lower rows become 0, things like this, and we have entries on this, and we'll see that. So how to do this? So in order to make this 0, in order to make this entry 0, this entry 0, so I'll take 2 of this whole row, I'll take multiply this 2 and then subtract it. So I'm saying I'll take 2 of the first row and then multiply it from the second row, and in order to make this 0, I'll just add these entries. So what I'll get is, so now I'll solve it. So what I'll get is, I'll get the first row as it is. So I'll get the first row as it is, like 1 3 3 2. I make it a little bigger, and the second now will get changed. So here if you multiply this by 2, so this is 0, so this will be 0 again. So this will be 6 minus 9, this will be 3, so this will be again 4 7, this will be 3. So 0 0 3 3, 0 0 3 3. Calculations can be here and there, but I want you to understand the concept. And again the third row, I'm just adding it together. So this will be minus 1 plus 1 is 0, minus 3 plus 3 is 0. Now we got 0 0 and then 6, then 6, 0 0 6 6. This is the first pivot, this pivot. And now I need to make other entries as 0, but you can see the second pivot became 0. Okay, we have no pivot in the column 2 basically. Okay, the second pivot has become 0. This is basically unacceptable, and we are trying to see if we can make a row exchange. I said you there is a curable case. Now you can clearly see it here. This is not a curable case now. This is not a curable because if we cannot make a row exchange, we cannot get some entry, some non-zero entry here in this place, because it was 0, so we cannot get this, we cannot row exchanges. But what we can do is we can keep on, what this echelon form says is you continue keep on doing this reduction. We call this reduction. So I'll probably make this thing as 0 also, or maybe I can do one thing. I can just multiply this by 2, so I can multiply the second row by 2 and just subtract it from this. So what I'll get is, I'll get 1 3 3 2 0 0 3 3. Whole of this row became 0. Okay, this is called as echelon matrix, this matrix. Do not lose the sight that we are solving Ax is equal to b. What I did is, I did the row reduction, what I called as, I continuously reduced the matrix. So we had actually Ax is equal to b. Now what I did is, I transformed, let's call this matrix as u, or let's call it as u. So I made u, it was 0, sorry, ux is equal to 0 now. Now I know that I haven't done, I've just performed elementary transformation. Whatever the values of x I'll get out of this u, so same values I can substitute in here and I can get the solution for this. So now you see that this is some sort of nice. So this looks nice to me because we got one row as 0. Okay, so this looks at least nice to me. Why? Because we have very less variables to solve now. So now here if you see that, you have how many variables, 1 2 3 and 4. So we have 4 variables. So if you are solving this equation like this, so you have 4 columns, we are solving it for 4 variables. So the equation here is again taking this, it was 1 0 0 3 0 0 3 3 0 2 3 0. Let's just multiply it by x1 x2 x3 and x4. This is what we want to find, and this was equal to 0. This is what we want to find. Now you know that for sure, you know that this equation, the whole of this, like x1 plus x2 plus like 0 times x1 is equal to 0. So you so there is a solution. So if whole of this becomes 0, this should also be equal to 0. Otherwise, if there is some other value here, so we cannot say that, like, because non-zero value is not equal to 0 value, if you see. So if we got some non-zero things over here and we got some things over here, so we cannot say like this 0 directly becomes equal to some non-zero entry. So again, just writing it in a smooth way. So I am trying to find the values of x1, x2, x3 and x4. Now you see that there were pivots. So we had these pivots, the first pivot and we had the second pivot which became 0. So what I can do is, other things, if you see here, there is no pivot. So I can just substitute some values now. Now I got two things. So I got pivot columns, and I got non-pivot columns, which we call as free columns. Okay, so how many types of columns did I get? I got two columns. I got the pivot column and I got the what is called as free column. So what I can do is, I can just, now in order to find the solution, if you want me to find a solution, I can just expand this equation first. I'm taking this in detail because I want you to understand, because many of the times you will be solving equations like this. So this is x1 plus 3 times x2 plus 3 times x3 plus 2 times x4 is equal to 0. This is the first equation because I'm just multiplying this with this. Again, the other one is 3 times x3 plus 3 times x4 is equal to 0, and the rest is zeros. So now what you can do is, you can sort of have this column and this column as pivot columns, because they are the ones in which our pivot is there, and these two are free columns. These two are free columns. If you see, column for a third and column for the free columns. What I mean by free columns is that I can put any value in there. So I can put any value in, let's suppose in x3 and x4, and I can get the values of x1 x2 and let's suppose I'll take like this. So what I'll do is, I'll say in the first case, for this x1 I'll take 1, x3 is 1, let's suppose, and we'll find the x4's value. So x3 is basically 1 is equal to 1. So now I can find the value of x4. If you see, x4 will also be equal to 1 if you just solve this equation. Okay, so I just had this x3, I put it as 1, so I got x4 as 1. So I can write x3 is 1, x4 is 1, and now I just will sort of include these values, x4, x3 is 1 1. So now I have x1 x2 other variables. So one of them I have to make free variable. So here I told you that there are two pivot columns and two free columns. So here I took, for example, this x3 variable as one free, and I took this x4 as pivot, because I got the x4 value by putting this. Now I can again substitute either x1 or x2 values. So either one of them I have to make pivot, because I have this x2 value now, x3 value now. In order to find the 4 or 3 values must be known. So what I am doing is, I am taking one value again. Let's suppose that we'll take this x2. So what I'm saying is here just a change of these things. So I'm saying let's make this column as pivot column and this column as pivot column, these two, and this as free. This is free and this is free. So these are free. So I'll just highlight it with the red color, and then red wala is pivot. So what are the pivot columns for us? So pivot columns if we have is let's suppose the first free column was x3. This is that x3 is free, and then x2 is also free. These are the free columns that we have. What are the pivot columns? Are pivot columns. So they are x1 and they are x4. Just keep a track of these things. So what I'm telling you is that you can give any value to this x1 and x4, and x3 and x2 value, it will get computed out of these equations. So let's take the first value of this x3 and x4. Now we have x1, x2, x3 and x4. Now you know that this thing is free. This thing x3 is free. Okay, and this x2 is free. Is it x3 and x2? I don't think x2 and x3. So again, which are the x1, x2, x3, x4? So free columns are x2 and x4. Sorry. So free columns here are x2, this, and x4, this. So x1 and x3. This is x2 and x4, x1 and x3. So this is pivot column, this is pivot, this is free, and this is free. Okay. So now I have to find the value. So for free variables, I can assign any value. So I can assign, in the first case, I can assign 1 and 0. So what I'm saying is, I'll assign some value to x1 because that's a pivot column to me, and x2 I'll assign 1. And for x3 I'll just fill that value and I'll assign 0. So that's the first thing I'll assign these. And then again in the second case what I'll do is I'll assign this as 1 and this as 0 and fill these values. Okay, now solving this equation. If you see, I have to solve basically this equation. This becomes a lot of jumble, but it's okay. I can just clear out this jumble. But bear with me for a bit. If you're not understanding anything, I'll just explain it in the first iteration, then I'll again go through it. So what I'm saying is I have two free columns and two pivot columns. So free variables I can give values, direct values. I gave 1 and 0 and I get 0 and 1 to this. Okay. So what I'm telling you now, I have to compute this x1 and I have to compute this x3. So if I put x4 as in here, I put it 0. So x3 also became 0. If you see, so x3 also became 0. So here in the case where this, so this became 0. So now this is 0, x4 is 0, x3 is 0. Then I have to put a value. I put the value 1 to this x2. Okay, I put the value 1 to the x2. So now x3 basically x1 becomes, so x1 plus 3 times, I just gave 1 to this x2. So this is equal to 0. So x is equal to minus 3. So here minus 3 is the value. So this is one solution of the null space. Is it clear? Just tell me first, is it clear? I found one solution, that is 3 minus 3, 1, 0, 0. This is one of the solutions that will satisfy this equation. So again, showing you the big picture. The big picture was we had ax is equal to 0. So what we did is we made it into ux is equal to 0. So this u was basically echelon form. So what I did is I had pivot columns and free variables. Okay. So these are two things. So here we had two free variables and two pivot columns. If you see, this column was our pivot column, the first one. The first one over here was our pivot column, and the third one again was a pivot column. Okay, because we have a pivot here and we have a pivot here. These are the pivots because we want to basically make the entries below them 0. And these are the free columns we had. So this is our free column, this is our free column, and this is our free column. So out of this I got these two equations after reduction. So I got two equations. So what I'm saying is to the free variables, to the free columns, I'm just giving some random values. I gave 1 and 0 to the, I gave 1 0. This is the value, and I get for the other solution I give 0 1. Let's solve for the first case. So I'm saying I gave 1 0. So the other values become minus 3, 0 and 0. So if you again check this a, so a basically was 1 3. Again let me write that a in the original form that we had. The original matrix was, original matrix we had is 1 2 minus 1 3 3 2. Let's randomly fill it. Just bear with me for a while. So the first solution that I found is this: minus 3 1 0 and 0, minus 3 1 0 and 0, minus 3 1 0 and 0. So if you see this, so is it equal to 0? So what is this telling me? This is telling me take 3 times this and negative it and take 1 time of this, okay, and nothing of these two things. So this should be basically be equal to 0 0 0. So if you take 3 times of this, so this becomes 3 6 minus 3. So if you again put a minus sign, so this will become minus 3. I'll just write it small. This will become minus 3. This will become minus 6. So this will become plus 3. So if you sort of add these together, it will be 0 0 0 and take 0 of these things. So that's what these things are telling me. So the first solution I got is minus 3 1 0 0. So this is the solution. Now if I multiply it with any scale, let's suppose I'll multiply it with c, so whole of this will become the solution. So irrespective of whatever I multiply the whole vectors with, it will still take it to 0 0. This is the first thing I got. Now the other thing that I told you, in the free variables I put 0 1 in the second case. In the second case, what I did is I put 0 1. So for this, again copying this equation, this is the equation that I got from row reduce this echelon form. So I'll just take this, copy this thing. So these are the equations I got after I reduced it in echelon form. So this is the equation that I had. Oh, sorry. I'll just keep it here. So what I'm telling you is that in the second case, these were my free variables. I just marked the free variables. If you again remember this, so this was my pivot, pivot free. So this is my pivot. This is again my pivot. Other are free variables. So others x2 and x4 are my free variables. So in the second case, what I'm saying is I'm saying for the free variables, what I'll assign 0 1. So I'll get something, I'll assign 0, I'll get something, I'll assign 1. So for the x4, I'll assign 1. For x4, I'll assign 1 value. If you see this equation, I'll assign 1 value. So x3 basically will now be equal to, if I just solve this equation, so x3 will be equal to 1 again, if you see this. Because this is 3 times of x3 plus 3 is equal to 0. I think this will be minus 1, I guess. So this is 3x3 is equal to minus 3. So x3 is equal to minus 1. This is what I get. So now I have the value of x4, I have the value of x3. So I put x1 plus 3x2, x2 is 0, it will be 0, plus 3 times x3, x3 is minus 1, plus 2 times x4 is again 1. This is equal to 0. I need to find the value of x1. So this will be x1 is equal, so this will be minus 3 plus 2. So this will be 1, it will be minus 1. So here if you see this will be minus 3, so this will be 2 plus this will be minus 1. So if you go again from the other side, it will become 1. So x1 is also equal to 1. So this value now becomes 1 and this is equal to minus 1. So this is the other solution for the equation. And now if you again multiply it with any variable, let's suppose b, that will be the solution. Now I told you that these two things are the solution to this. So in the null space, we had two vectors. So we had vector 3 1 0 0, I guess, minus 3 1 0 0, minus 3 1 0 0. And the other vector that we had is 1 0 minus 1 1. These are the two vectors that we have in the null space. Okay, and because I changed, this is the one variable 1 0 and this is the other free variables that I had. I just put the equations over there. I told you that any combination of these two also should be in the null space. If we take any combination of these things, that should also be in the null space. So all the so here if you know this, so this 1 0 0 and 1, it makes identity. It makes an identity equation. It makes an identity matrix. So here if you tell me what is in the null space of A, so I can tell you null space of A contains, let's call this vector now as v1 and call this vector as v2. I'll say C v1 plus d v2. This is the whole null space of this vector, of this matrix A. Is it clear? Maybe it was a little bit mouthful for you. Just tell me, is it clear? Otherwise I'll just go through it once. Or why are you sleeping? Rian?
Yes, sir.
So my job was to find the null space of an equation. Sorry, null space of a matrix. So what I did is, so I just reduced it to echelon form. So in the echelon form, what I did is I got some free variables and some pivot variables. Pivot columns are those columns in which I had those pivot entries, and for the other entries, these were free variables. So it was quite clear for me. So there were only two columns in which I had pivot left. So one is this, if you see the equation. So one was this column because here we had a pivot, and in the second the pivot became 0. So this was a free column again. In the third we also got a pivot. So these are our pivot columns. So in order to get the answer, I just assigned some free values to these free variables. So from that I got one solution. So I assigned 1 0 to the free variables, and I got values for other pivot variables. And in the second case I assigned some other values. So this is not actually random. This 1 0 and 0 1 is not random, because I know this 1 0 and 0 1, it is basically standard basis of this R2. That's the reason I chose these values. So I told, if I multiply this with any combination, if I multiply this with C, any variable, so that will also be in null space. So if I also multiply this with any scalar D, so that will also be in the that will also be in the null space. So if I take the linear combination of these two things, that will also be in the null space. So if I want to compute null space, I just have to give the free variables as values that I give in the identity matrix, and just take the linear combinations of all the values. So this is the null space which I computed. Is it clear?
Yes, sir.
Nice. So if it is clear, so we'll again go to what's called as row reduced echelon form. It's nothing special, just we have built this row reduced form. Now we'll again just take a row reduced echelon form. So in that, what we'll do is, so we had this equation in a row reduced form. The equation basically was this. If you take, this is the equation that we had: 1332 0033, 1332 0033, 1332 0033, and then 0000. This is our echelon form. So if you want to get it into row reduced echelon form, what is that? You know that these entries also can be made 0, maybe, or 1. Sorry, if they cannot make it 0, but they can be made to 1. So I'll just divide it by 3. So dividing by 3, I'll just get these entries as 1 1. Okay, now if you see that, this is our pivot column, this is also our pivot column. Okay, now if I just write them in a certain order, so I'll just write this as 100 as it is the first call, and then I'll exchange these columns. So 3 1 0. Okay, let's write it like this. Okay, also maybe I can do one more operation before writing this as like this. I can do one more operation. So what I'll do is, I'll just make this entry as 0 as well. I can make this entry 0 as well. Just subtract 3 times this. So what will happen is, this entry will remain as it is. So 3, and this will be struck off. So this will become 0. So 3 times of this. Now 3 times of 1, and then 2 minus 3, so this will become -1. What I did is, I just multiplied this with 3 and subtracted it with the other equation. Just going back. So what I had this was my equation. So I had multiplied this equation by 3, and that's R1 subtracted by 3 times R2. So what I did, this became 1 minus 0 is also 1, 3 minus 0 is again 1, again 3. Then we had 3 minus 3, this became 0. I'll put it like this. And then after 3, I had 2 minus 3, that's equal to -1. So I changed these. And now I know that this is my pivot column, this is my pivot column. So I'll write it like this: 1 0 0. I'll take the pivot columns on one side and free columns on the other side. So 0 1 0, 3 0 0, -1, 1, and 0. Okay, so now these are my pivot and these are my free columns. Okay, this is what I get. So I can write this equation like this: P and F. And now you know that this P basically is identity. You saw that I got an identity at this point. So I can write identity instead of pivot. And what is the solution? So solution basically can directly be written as like this. So I can put I over here and minus F. Okay, if you see the solutions in here, if you see the solutions, again see the solutions. It's a really important thing. The solutions were -3 1 0 0. Okay, then we had solutions as 1 0 1 1. These were the two solutions and the combination of these things. So what I can write is, the solutions basically are identity. So I'll write 0, I'll write 1 0 0 1. So this is our pivot columns. Then I can just add the free variables. So where are the free variables? So this is our free variable. So these are free variables. So I can add these variables, but they'll go on the other side of equation. That's why they'll get negated. This 3 will become -3 because it will be on the other side of equality. So this will become 3 0 1 -1, 3 0 1 -1. So this will become 3 0 1 -1. So this will be a matrix and it will be multiplied with C and D. Okay, now this whole is again null space of A. So if you see the answers over here, 3100, so that's the answer we got. Sorry, it should be minus 3100 because we have to change the sign. So minus 300, other one should be 10 minus 11, 10 minus 11, 10 minus 11. That's the answer we got. So what we did is we just perform an additional step. The additional step was that we are changing it into again and the row reduced echelon form. So the first form was just echelon form. The second form is that row reduced echelon form. Is it clear?
Yes, sir.
Okay, I think my space is a little bit less. So what I have to do is I have to basically cut this video. Maybe I'll paste it onto some other location. Okay, because space left is really less. It's giving me so this is 23, 12, 24. Oops. 23, 12, 17, right? So what have I pasted? Just bear with me for maybe 1 minute so that this recording will not be wasted. Oh, nice. Okay, I got some free space as well. So it actually was giving me this notification that the drive actually became empty. I didn't want to lose this recording because it was a really important lecture. Right. 164. So what I did, FLV, this is 164, 164. Right. Nice. So are you with me till now? Or have you slept already?
Yes, sir.
So who is there? Everybody is there? Yes, everybody is there who I'm expecting. So nice. If you are understanding this, so what are we finding? We are trying to find the row. We are trying to find the answers to this. Ax is equal to 0. We are trying to find the answers to Ax is equal to 0. So what I told you is that we'll reduce it into a row reduced echelon form. Okay. So in that, what we'll get is we'll get an answer like this. We'll get identity, then we'll get some free variables, and the answer basically will be minus free variables and I. This will be the answer and multiplied by this linear combination, whatever the linear combination will be. So this will be our answer to this. This is our null space of A. Okay, and you will be given in assignments questions like this to find the null space and stuff like this. Is it clear? Is it clear?
Sir.
Should you do another example, or can you do it on your own now and you will rewatch the lecture maybe?
Sir, we will do it.
Nice. If you will do it, then we need not to go through the other example. Now the question remains. The question that we have is how to find this. How to solve this ax plus ax is equal to b. How to solve this ax is equal to b. I told you that now we know how to basically get null space of A. That we saw how to use this row reduced echelon form and stuff like that, and we were able to get this free variables, pivot variables, and we were able to solve it. Now you got these. Now you have this special. Maybe we call this a special solution. Special solution. This is special solutions. Now we need to get a particular solution. If we get one particular solution, let's suppose if we get a particular solution, then we'll add these null solutions and we'll get all the combination of solutions. So that's the point. The whole point is that if you want to get a complete solution, now you know how to get this null of A, how to get this null space. Okay, you have a method for that. You will row reduce in the echelon form, and then you will get it. Now you will find a special solution as well. So in order to find the special solution, again you will have to go through the process. So let's suppose you again will do this thing. For example, now this ax is equal to b. So what will happen now? If you reduce it into the echelon form, you will reduce it into maybe ux is equal to c, because this will get changed also. Okay, you will reduce it into something. So in our case, if I just took the example that we were dealing with, so in that, let's suppose we had 1 3 3 2, and then what was the other thing? Maybe I have written it somewhere. Let me find it. So then we had 2 6, 9, 7, minus 1, 3, 3, 4. So we have to reduce it, but it was now it is equal to, let's suppose, b1, b2, b3, and this is it. This is what it is equal to now, b1, b2, b3. Okay, this is the solution. Now I want to find solution for this. So here we had this UVW, or maybe x1, x2, x3. Maybe I will write that x1, x2, x3, x4. This is the equation. The first thing that we want to get, we again want to get into echelon form, that u. So you know that what is the echelon form. We got that echelon form previously. So that echelon form basically was 1, 3, 3, 2, 0, 0, 3, 3, 0, 0, 0, 0. But we have to perform the same operations on this. So we have to perform these same operations on b1 as well. So we have to change that b1. So this is equal to, this is x1, x2, x3, and x4. Now you have to change this b1 and b2. The first remained as it is, b1 remained as it is. To the second, what we did is we took basically this row, multiplied it with 2, and subtracted it from this r2. So this basically becomes b2 minus twice b1 for this operation, because that's how we struck off these entries 0 and 0. And for the other row, what we did is, for this, because we became 0 and we performed operations, these operations basically were b3 minus twice b2 and then plus 5 times b1. This is how we got the whole row as 0, this whole row as 0. This is the operation that we got. Okay, is it clear so far? Because initially we were solving ax is equal to 0. Now we are solving ax is equal to b. So the operations that we performed on this above matrix, the same operations will be performed on this. That's what I did. So as this row remained unchanged, this row also remained unchanged. Similarly, for the changes that were done to this row, so this the changes were also done to this, and similarly changes were also done accordingly to this. This is what we got. Okay, so now we got ux is equal to c. This is our u, this x is as it is, and this is our c. Now this is what we got. Okay, now we need to see, the first thing is we need to see this. So if you see this equation, so this basically says 0 is equal to, and this multiplier 0 is equal whole of this thing. This says 0 is equal b3 minus 2b2 plus 5b1. This is what this thing tells me. Okay, is it clear? Okay, is it clear? Then I can move ahead. So it is not clear whether these equations have a solution. The third equation basically is in doubt. The third equation basically says b3 minus 2b2 plus 5b1 is equal to 0. Okay, we'll have to get values in b1, b2, and the second equation basically says, second equation here we have this thrice of if we take this thrice of x3 and 3 times x4, this is equal to this one. This is how we can expand it. So now we have this. So columns of a, the columns of a, right, that we have here, they basically can span 1 to 1, 3, 6, 3. So we have to find the values now. So if we took this, so here we have a doubt then whether whether the solution exists for this. So because even though there are more unknowns than the equations, there may be no solution. So here you can see that equations are only 3, but we have 4 unknowns. So even though there are more unknowns for that, and there may be no solution for that, so we no another way of answering the same question if we solve for b. So what we do is we can find the column space of this. We can find column space of a. Okay, we need to find the column space of a. So in the column space, if you know that in the original equation was 1, 2, minus 1, 3, 6, minus 3, 3, 9, and 3, 2, 7, and 4. This was b. So this is what we had, the equation we had initially. So this was our equation. These are the equations that I wrote, the original matrix. So if I have these as columns, so if I take all the combination of this, so this is column space of a. So I'll take combination of all of these columns. So this basically will give me columns of A. So column space of A. So the CA basically is described in two ways now. So the first thing is we have these 4 columns for which I'll take linear combinations and I can create a column space out of this. And then we have a constraint, and the constraint basically is this b3 minus 2b2 plus 5b1, it should be equal to 0. That is some sort of constraint on me. So I'm saying you have to solve these equations, but this should be the constraint. Okay, this should be the constraint that I have. Is it clear? If this is clear, I can move ahead. So now you know that. Now what do you know is this 130 is actually a solution. So if I take, for example, any column from this, so I have, let's suppose 1 2 minus 1 is a solution. So if I say 130 is the solution, so we can get all the solutions like this, and we'll get to, basically we need to get the complete solutions. We saw what is the solution of null space. So in the null space we got some solutions. So now we need a complete solution. For that we need a complete solution. So we are saying this ux is equal to c, basically tells us that if we say 1 3 3 2 0 0 3 3 0 0 0 0, this is our u, then our x is x1 x2 x3 and x4. Now this is equal to b, because you know that this is in the column space. 130 is in the column space of A. Now we can solve it for this. As you expected, this last 0, it should be 0. So I just gave some random values 1 3, because 130 should be in the column space. So 130 should be in the column space of this, because here you saw that this 0 should be equal to 0. If this 0 was equal to not 0, then game over. We cannot solve the equation. If here it was a it was a non-zero number. So I put 130 in such a way so that it becomes a solvable equation. So if there was some other number in the column space, then we cannot solve it. So here we have this 1 3 and 0. So now I can expand these equations again. I can expand. So this will be x1 plus 3 times x2 plus 3 times x3 plus 2 times x4. This is equal to 1. And the other equation I'll get is 3 times x3 plus 3 times x4. That basically is equal to 3, and the rest is 0. So these are the two equations I got. Okay, now you can say, you can basically solve these equations. Now you can again solve this equation. So these are the equations that we got. Now you can solve this for this particular solution. For example, if we have a solution 130 is a particular solution that we have, and you can solve it for this. So if you solve it, if you find some values of x1 x2 x3 and x4, and now you can do it. And the solution, for example, let's suppose is we have this -2 0 -2 1 0 0. So again we have to assign free variables and pivot variables. So the same concept here. So we got one solution. Let's suppose we'll take again x1 x2 and x3 and x4, and these are our pivots. X1 and x3 are pivots. So what we'll do is, for the free variables we'll assign 1 0, or maybe we'll assign 0 0. It is up to us. So we can assign both the 0 0. So when we assign 0 0 the values, so here the values we'll get for x3 and x1, it will be -2 and 1. So this is one particular solution. So we got one particular solution. We got -2 0 1 and 0. So this is one particular solution that we got. And you know that the null solutions that we got were -3 1 0 0, and the other solution that we got is 1 0 -1 and 1. This was the other solution. So we took the combination C and D as well. So now with this particular solution we can add it to the null space. So this will give us the complete solution. Okay, is it clear? Is it clear how did we got the how did we got this particular solution? Again, to reiterate it, so what we did is we took this matrix again, made it into the row echelon form, then took a particular solution so that it satisfies. So the particular solution we took is the vector which is actually in the column space, that is 130. If it was something other than 0 over here, then this equation won't be satisfied. So there was no solution, but we took on purpose a vector which will be solved by this. So it is like, take one of take for example some vectors which can produce 130. So 130 can be produced like this. So the first thing is 1, second thing should be 3, and other thing should be 0. So for this the values basically were -2 0 1 and 0. So that is, take -2 times this. Okay, the -2 times basically take this, and then take 1 times this and other 0 0. So if you again see it, take -2 times this and 1 times the other 0 0. So this will become -2 and -2 0 0. So this will become 3 0 0. So if you sort of add them, so you will get this number. That's why I just took a particular solution, and this was the values for the variables for that particular solution. And as I computed the null space as well, for the null space I had these two solutions and all the combination of these solutions. So this was our special solution. So this was our particular solution. So after combining both of these, we got the complete solution for A. So basically what we were solving, solving AX is equal to B. I think we have 10 minutes left, so I'll just wrap the things up quickly. The things that we discussed in this lecture is, we were trying to follow sort of solve this. So for this, we told we'll break into two things. So we'll find a special solution and we'll find a particular solution. Particular solution. So what particular solution was? So we'll find a special solution, that is ax is equal to 0. We'll find this is what we'll find, and then we'll find some axp is equal to some, let's suppose b. That's what we'll find, or maybe some b dash or something. We'll find a particular solution for this b. We'll find one particular solution for this b. So this is our particular solution. So this null solution, basically in the both things, what we did is, the first thing is we reduced it into echelon form, and here the same thing was done. We also reduced it into echelon form, and from the echelon form we get those free variables. Here we got, and the two steps, we got pivot variables and we got free variables, and we assigned the values to those, and then we got, if we had two pivot variables, and we just wrote them over here, and then we got another pivot, we got wrote them here, and then took the linear combination of these. So this was basically the null space of A. And in this case, so what we did is, we wrote a particular solution 130. It was a general solution which we thought that it is in the column space. So by using this 130, we got a particular solution, a one particular solution. This is our particular solution. This is our xp. Okay, so now then what we did is, we added this xp with this xs. So this is our xs. All these solutions are xs, xsp, let's suppose this is xsp. So these two solutions when combined linearly, so we got the s complete solution. Is the process clear now? If you have to solve ax plus b, the process is to break down into two things. The first thing is find the null space, find the null space of this. We call it a special solution, and also find a particular solution. Why it is called particular? Because we just set this particular b, we set it as 130. That's what we set it in, and we found some xp. We found a particular solution, and in this we found a null space. Then we linearly combined all of these solutions. Okay, when we linearly combined all of these solutions, so what we did is, we got this complete solution. Is it clear?
Yes, sir.
I think if you want me to go through other example, so we can do that. But I hope that in the assignments you will find these particular solutions, and you will find these special solution, and then find this complete solution for the problems. Then that will be really easy for you. If you again go through this video, if it became a little bit harder for you, again rewatch the things so that it becomes clear for you. Is it clear?
Yes, sir.
Yes, I'll in the last few minutes, so I'll see if there is some space error. I don't think that should be the case, but still I'll see. Oh, no, yes, that's working perfectly fine. So what I'm telling you, that I'll just reiterate the things that I have been telling you from the previous lectures in last maybe 10 minutes, so that in the next lecture you will be quite clear with this. The concepts that I'll again go through is linear independence, because these are required for the next lecture. And then I'll also go through the basis, concept of basis, and then I'll also go through one more concept known as rank, and I'll also go through one more concept known as dimension. These are new things to you, but these things that you have studied. So in linear independence basically means, if you have vector v1 and you have some vector v2, you have some vector v3, and so on. So if you sort of take linear combination of these, mathematically speaking, a times a1 v1 plus a2 v2 plus a3 v3 is equal to 0, only if all these ai's are equal to 0. That is, basically all the vectors that are present in this v1 v2, we should not be able to get these vectors from the combination of others. As you saw that this 1 2 3 4, they are linearly independent vectors. But these vectors 1 2, this is the vector, and 2 4 is a vector, but you know that you can multiply this vector by 2 to get this vector. So this is linearly independent vectors. Okay, so linear dependent and independent is clear. So now then we have bases. So what are the bases? If we have a vector space, now you know the concept of vector spaces. Now there are a bunch of vectors in vector space. So there are some special vectors. If we have some special vectors like v1 comma v2 comma v3, if these are the vectors, and if these vectors were able to span whole the vector space, what's the meaning of span? If we were able to get any vector v, if this is a vector space v, if we took a vector small v from this vector space, and if we were able to get this v by taking the linear combination of these three vectors, we call these three vectors as bases. Okay, so for example, in our R2, the basis standard bases were 0 1 and 1 0. So by using these two vectors, you can sort of create any vector. So there's a concept of basis. The number of vectors in the basis, so this is called as dimension, because there can be infinite bases. So 1 0 0 1 is one basis, let's call it b1. So you know that we can consider any two independent vectors, 2 3 9 8. This is also basis, this is also basis, we call the standard basis. We can have b3, let's suppose any two random vectors, 4 5 6 9. This can also be basis, but the special thing about these bases is that the number of vectors in these bases is only 2. This is for r2, especially I'm speaking about r2. For all the basis vectors there can be different bases. So here we have one type of base, we have another basis, we have another basis. But the special thing about these bases is that the number of vectors present in this basis is always equal to, it is always equal in all the bases. So here it is 2 for r2, in r3 it is equal to 3. So the number of vectors present in the basis is called dimension. So what is dimension? Number of vectors present in basis set. So bases are the vectors which span the whole vector space. That's the basis. And if you call what is rank, the rank basically means the number of pivots. We have been seeing the pivots. We have been seeing in this equation we had two pivots. When we reduced it into the echelon form, that time we got these two pivots. This is our pivot. This is our pivot. So the number of pivots we'll call it a rank for now. So rank basically is number of pivots. Okay. So these are the definitions that I want you to sort of by heart and know these definitions before going to the next session. Why? Because they will be used in understanding what is known as like projection on subspaces and the things like that. The first is linear independence and dependence. All the vectors, if they are linearly independent, so no vector can be formed by the combination of other vectors. So that's what I mathematically wrote here. So if I have vectors v1 to vn, so if this equation will only hold if all the coefficients become 0. Otherwise, if there is a non-zero coefficient, that basically means that you can form a vector by using the combination of other vectors. So no linear combination should be possible to find a vector in that set. That's the linear independence and dependence. Got the spanning? Spanning basically means if there are some vectors from the linear combination of these vectors, you are able to reach every other vector. We call that set of vectors will span that vector. So if I say if I'm saying you R2, so this is a vector R2. Let's call this is a vector space. So I'm saying that 1 0 0 1 is able to span this vector. What is the meaning of that? That means we can reach any vector in R2 by using these two vectors. So this is the concept of spanning. And the minimal spanning set. So minimal spanning set is known as basis. So minimal spanning set means that there are a lot of bases now. There can be other vectors for, but if it is minimal and it's spanning the whole vector space, we'll call it a basis. And you can have greater than one basis. You can have a different set of bases. But one thing that is common in all the bases is that the number of elements in all the basis sets is same. So we call that number of vectors present in bases. We call that dimension. Okay, that's the concept of dimension. And then the rank is basically when you reduce that matrix into the row reduced echelon form and maybe echelon form, we get the pivot variables and the free variables. The free variables basically tell us the rank. We call it a column rank, or maybe we'll also see what is a row rank. As of now, just remember that this is what we call as a pivot. Is it clear? Is everything clear so far? Maybe it was a little bit heavy lecture on you guys because you are not sort of accustomed to see the mathematical details, but the reason I am taking this is that so that you become really good at these fundamental aspects of linear algebra, that will be the building blocks for machine learning and deep learning. So that whenever you find a problem, so you'll directly see, okay, this is where it comes from. So because the machine learning, deep learning, this basically was discovered in 1900s due to the math, but we did not have machines that time. But when these machines and hardware became, and it grew, and then afterwards we were able to use this technique. If you see the famous algorithms, they were made in 1950s, 1940s that time by using the mathematics. So all these techniques were present in the mathematics. But the two things that were basically missing from that era, the first was data, the second thing was the compute power. When we got this compute power and when we got these data, and we were able to basically recreate everything that we sort of imagined at in 1940s, 1930s. Most of these algorithms are discovered before 1980s. If you see algorithm of this linear regression, logistic regression, support vector machines, they are before 2000. Every algorithm, even back propagation, that is the workhorse of this deep learning, each of this was mathematically discovered before this deep learning and machine learning became famous, because whole of this was dependent on having a lot of lots of data and having a lot of compute power. And that the compute power and the data, it was generated, I think, after 2000s. So now we are in the era in which the algorithms are there, and now we have compute power and we have the data as well. So and we are in the golden era, some sort of thing. So everything fell in place, and now we are able to sort of gain the things out of this machine learning and deep learning. So is this clear? Why am I teaching you the things in this depth? Because I want you to feel that you can do machine learning with the hand. You can do machine learning on your fingers. If somebody says you can you making classification algorithm, you can say yes, I can make it on my pen and paper. And maybe if you want to make it faster, you can use the computer faster calculations. Because I am not a calculator, I can give you the algorithm, I can give you the intuition of the maths behind it. And then if you want to make an algorithm, if you want to make a better algorithm, which will perform faster than my hand, maybe you can feed it to the computer. That's how I want you to see machine learning, deep learning, and stuff. Is it clear? Nice. Maybe I'll stop recording and I'll